12.5, lines and planes in 3D or higher, actually. So this is what we want to do in this section. So what we want, to find the equation of a line in R3. So in the three-dimensional coordinate system, or 3D, 3-space, we want to determine how to describe a line. So just a little recap. In 2D, R2, you already know some of this stuff. You have y equals to mx plus b. So you have that form. You have the standard form, ax plus by equal to c. Keep in mind, you already know this. M is the slope of the line, right? So we're going to have an analogy to the slope of the line for lines in 3-space. Now, if I just add another variable, right? If I just say, so you have x, y. What if I add z? What is that? Is that a line in 3-space? What does that do? Well, as you know, that actually creates a plane. So that's not what we want. We don't want 3 variables because that'll create another dimension, which creates a plane in 3-space. Okay, so we're going to define it by, I already drew the picture below. So draw, if you have a moment or want to pause it, draw this picture, and then I'll go through and label it as we go. So here's the derivation of a line in 3-space. So we're going to let v equal the vector a, b, c. So that is this vector here. So this is the vector v. Okay, so that is, so b, a vector parallel to the line L that passes through okay, and just real quick here. So we have a line L like this, okay, in space. So we're going to describe that line. So v is the vector that's parallel to that line. So you picture a line in space up there, and then you can have a component vector that passes through it. I mean, that is parallel to it in any direction. Let me finish my statement. So through the line L, now the line L passes through a specific point. That point is x1, y1, z1. Okay, so that point is here. So that's the point that I drew right there in yellow. Okay, so this point P is your specified point. And if you have a direction and a specified point in space, then that's all you need to define a unique line. Okay. So let me finish my statement here. So V, oops, let me change it back to white. V is called the direction vector for L. So it's called the direction vector for the line L, or just for L. So then this is how we're going to define it. So we have a bunch of points, arbitrary points on the line. That's your Q. So we're going to define the line L to be the line that's through P parallel to V, and it's the set of all points that's true. It's like you have the same direction. So this is how the statement goes. So the line L through the point P parallel to V. So parallel means scalar multiple, okay? Parallel scalar multiple. That is the set of all points Q of X, Y, Z. Those are arbitrary points such that P, I changed that and I don't want to change that, such that PQ is equal to TV. Where T is arbitrary, right? And T is in the reals. That's your scalar multiple part. So that's what we mean by parallel. So PQ is equal to, so PQ, we're going to make that into, write that as component form. That's X minus X1, Y minus Y1, and Z minus Z1, right? Remember, it's terminal minus initial. I put too many commas in there. So that is equal to T times the vector V, which is A, B, C. So if we distribute that across, you end up getting TA, TB, and TC. So now we just equate components, and you show, or you have that X minus X1 is equal to the TA, and then we have Y minus Y1 is TB, and then we have Z minus Z1 is TC. Just need to put a 1 there. Okay, so now equate components. That's what I just said basically. Now equate components, and you have X minus X1 is equal to T times A. Y minus Y1 is equal to TB, and Z minus Z1 is equal to T times C. And that's your parametric form. So we call that parametric equations, or form of a line, is how you would say that. So you have X equal to X1 plus TA, Y equal to Y1 plus TB, and Z equal to Z1 plus TC. Okay. So that's your parametric form of a line. All right, so let's look at an example of how to do that. So here's an example. So find parametric equations Oh, and I almost forgot to write that your t is anything. So where t is any real number. That's what basically makes it vary for the line. All right, so find parametric equations of a line through the points P1, 1 to 1, and P2, which is -1, 1, -4. Okay, so you have 2 points in space. You don't need to like write them, but basically what you do first is construct your vector v, okay, out of those 2 points. So you basically create your direction vector. So if we do the point, the vector, so v is equal to P1, P2, and it doesn't really matter the order. So you construct that, so you'd write -1 minus 1, 1 minus 2, and -4 minus 1. So that is the vector -2, -1, -5. Now, it doesn't matter what direction, right? Because you're going to multiply by a constant anyway, that t. So you can choose your direction vector. So we're going to, and by multiplying by a scalar. So choose v to be instead just 2, 1, 5. It just makes it look nicer. So from there, it's pretty easy. You just read off the points. So this is your A, B, and C. And so you just need a point, x1, y1, z1. So either one of these are the points you choose. It doesn't matter which one you choose. Okay. So we have x equal to, and I'll just pick the first point, so 1 plus 2t, y equal to 2 plus t, and z equal to 1 plus 5t. So here are your coefficients. Your A, B, and C are the ones there in pink. And then these points is the point given. Here, here, and here. And you could use the other point. So you could put this point there if you wanted to. And it's all the information of the direction is already there. So this is your ABC, so it's contained in that. So it's like your direction vector is like slope. So you kind of think of this as slope. So let's put it here. So that's like the slope of a line. Okay, let's do another one. So next question, next example. Okay, so this is basically working with parametric form and then doing some calculation. This one's pretty straightforward, but here's the idea. So let L1 and L2 have the parameterization like this. So L1 is x equal to 1 plus 2t, y equal to 3 minus 4t, and z equal to negative 2 plus t. Then L2 is x equal to negative 5 minus t, y equal to 2 minus 3t, and z equal to 4 plus 3t. All right, so the direction of this one is pretty straightforward. Find the angle between the lines. So find the angle between the lines, L1 and L2. So if you have two lines, so picture two lines in space, right? So you have a line like this and a line like this, but they don't necessarily cross each other. But if you put it in like the same plane, then they're going to have an angle. That'll be some angle theta. This will be 180 minus theta. So what you do then is find the angle between the direction vectors. So how to do this is, what we do is we find the angle between, I'll just say V1 and V2, those direction vectors. Okay, and then we're going to use our special formula. We're going to use u dot v, the one we derived, magnitude u, magnitude v, cosine theta. So we're going to use that one and just solve for cosine, and arc cosine will give us that one. So try it now. Okay, so try it. And then we'll come back to it. Okay, so what we have then, so write down V1. So you look at the coefficients of V1. So here's your coefficients. So that's your ABC. So that's 2, negative 4, 1. And then your V2 are the other coefficients. Negative 1, negative 3, 3. So negative 1, negative 3, 3, like that. And then V1 dot V2, we need that calculation. We need their magnitudes, magnitude of V1, magnitude of V2. So do all that. So you do the dot product, you get what? Negative 2 plus 12 plus 3, which is 13. Magnitude V1, square root sum of the squares. So that's 4 plus 16 plus 1. So root 21. And then magnitude V2, square root of, where am I at? 1 plus 9 plus 9. So that's the square root of 19. All right, so then you just do your calculation. So theta is arc cosine of, and you just, so that'll be what? The dot product is 13, and then over those, the product of the 19 and 21. So it's basically root 21, root 19. And so you can get approximation if you like. No big deal there. That's 49.4 degrees. So it's about 50 degrees. So when we look at lines, you have two different lines in space, then if this is theta and this is theta, the angle between the two lines is, you just take the angle between the direction vectors. This is 180 minus theta, of course. What else do we have? So parallel lines, like that. So if you have two parallel lines, those aren't quite parallel, are they? So parallel lines, they're same. Well, I'll write it down. So parallel lines, V1 is going to be a scalar times the other one. That's what we mean by parallel. And then what about perpendicular vectors? So we have two vectors that are perpendicular. What do you know about them? Like that. So if this is V1 and V2, we know their dot product is 0. Okay, so those are all the little pieces we need for this one. Okay, I think that's it. Next, we're going to derive a formula for the distance from a point to a plane. No, point to a line first. Point to a line.